Today we're very lucky to have Erik Tollerud here today to tell us about the community developed software model for Astropy and JWST.
All right, cool, thanks. Right, so I'm here to talk about sort of the new mode of developing software that in many ways JWST has embraced, but it was pioneered by the Astropy project. So before I can talk about sort of a new mode of developing software, though, I just want to give you a sense of what I mean by new, right? I mean mostly in contrast to what you might call traditional software development approaches that astronomy has made use of. So I sort of categorize these into two different things, which probably many of you are familiar with. One is the sort of large-scale, monolithic, if you like, development approach. So this is probably made most famous by IRAF, but there are plenty of other examples of large projects that were planned in sort of a project management way, typically developed by software developers rather than astronomers, but usually with at least some crosstalk back and forth, but still large scale, run by some institution, right? So that's what I'm calling monolithic. And the other mode of astronomy programming that probably most of us are used to encountering is what I'm calling lone wolf programming. Right, so this is what all of us do to some extent when we're doing science. We sit down and we just write up some code and we say, oh, all right, that's interesting. And maybe we say, all right, I'll put that up somewhere. Right, so this has been used for a long time. This is the primary method used for people using IDL, but it's also common for other languages. But the point is, both of these approaches have their drawbacks, right? As is probably well known from the fact that two of these three logos are essentially defunct. It's very difficult to maintain momentum on one of these top-down approaches, right? If the institution that's driving it decides to give up or the community decides it's not a priority anymore, these things can just wither away because without that large amount of support, they can't do anything. By the same token, while of course by yourself programming is a critical element of all work in astronomy, it tends to lead towards a lot of different packages doing the same thing. As you'll see, this is exactly what drove the development of the community model that I'm talking about, but it's a key thing that is very common in astronomy, right? So you have to keep this in mind as being the sort of starting points for what drives this community development model that I'm about to describe. So these were the common modes that I think have been done for essentially since the beginning of computers being used in astronomy, but a big change happened relatively recently. Catalyzed by this fact, right? The simple fact that Python has been taken up as the primary language in astronomy. So Eva Mamcheva and I did a study on this a couple years ago that demonstrated that, in fact, at basically all levels, Python is now the most used programming language among astronomers. So because of this, because open source is sort of in the genes of Python on some level, and this community developed model is how Python, the language, was developed in the first place, I think that, plus the sort of development of all of the tools I'm going to describe to you today, led to this new community-driven model that is sort of exemplified by Astropy, but is becoming more and more common in astronomy, particularly, in many ways, being embraced by JWST. All right, so that's sort of how the story of what I mean by sort of community-developed software. But now I want to give a more detailed case study of what this really looks like. Right? Because all that is very abstract. Right? So the case study I'm going to provide is the one that I'm most familiar with as one of the Astropy Coordination Committee members, and that's Astropy. Right? So we're going to spend a little while talking about how Astropy came to be and how its version of this community-driven software development model operates as a window into both how it can help JWST and how hopefully the wider community can contribute back to both JWST and all of our shared efforts. So let's talk then about how Astropy came to be. So that's the starting point here. Astropy began in 2011, essentially driven by the essential question along these lines, right? Not just this question. There are many other questions you might ask in astronomy, but a lot of them, when you wanted to answer them with Python, you had to ask, how do I do this thing? And the answer was, there are a lot of ways to do it, right? You want to do this relatively straightforward task of converting from equatorial coordinates to ecliptic coordinates. And there were at least, what do I have there? 6 different libraries. Actually, I think when I counted this more completely, it's at least 10 different libraries that implement that very standard astronomy technique. So this ends up meaning there's a lot of wasted effort, right? At least 10 different people all did the same thing. Maybe 2 of them are sort of subtly different in ways you need to worry about, but certainly there aren't 10 different ways to do it. On top of that, you can't pick and choose tools, right? They're mutually incompatible. They don't work together. So not only have you wasted a lot of effort, you've also scattered the community into tiny little fiefdoms where they can't work together. And since, in many ways, collaboration is the essence of astronomy, this creates all kinds of weird sociological problems. So that drives the idea that you should work together. And in fact, I think everybody in the sort of Python developer community at that time recognized this. And it's important to understand, I think, that this is one of the key elements to making this community-driven software model work. There has to be agreement that this is worth doing, that this is something that everyone needs to get on board with. Otherwise, it's not going to happen. But everyone agreed on this, right? So in June 2011, Marshall Perrin, who is at part of the JWST mission at Space Telescope, asked this simple question on the mailing list that's sort of the go-to mailing list for doing astronomy with Python. Basically said, do we really need someone, it may or may not have been me, tried to introduce a new sort of shared set of libraries, and Marshall quite reasonably asked the question, do we need another one of these packages that all do the same thing? And everyone said, probably not, right? And this had been said before, but for whatever reason, this particular time the question was asked, all of the momentum gathered up and things actually started happening, and that's what led to ASTROPY, right? So everybody agreed this was a problem, and everyone understood this problem needed to be solved, and that time the question was asked, the result was a real effort that turned into the ASTROPY you see today. It began as sort of a grassroots discussion on the mailing list of, okay, how are we going to work together on this? And then a series of votes by some 100 people, and then critically some initial development work on the sort of plumbing stuff that a lot of people don't really want to do by Space Telescope programmers, working in many ways on building the underpinnings for JWST. So that was the result, and the result of that was the ASTROPY project that sort of exists today. At that stage, it was really just a vision, although it's interesting to look at this vision because it looks a lot like the ASTROPY that exists today. If you're interested, you can see the link down here. You can read the document, and it really looks like what we imagined with no code in front of us and without this community actually came to be, which I at least find rather astonishing. So that's how it started. All right, but what is it, right? What does this community development model look like? To understand that, you have to understand what's the philosophy behind ASTROPY'S version of the community development model. And it's basically this, right? It's a community effort to develop a single core package for astronomy and foster interoperability. So this means really 2 different things, right? This community piece, it turns out, ends up meaning 2 very different but very important things. It means it has to be both by the community and for the community. Right? By simply means the people who are using it, the astronomers, help write the code, right? They're involved in the process from the beginning to the end. You'll see what that looks like in just a second. But it also means it has to be for them. It has to be useful to them. It has to be something that they can use every day. Right? So those are sort of the 2 key pieces of what community-driven software in this ASTROPY philosophy looks like. So I'm going to start by talking about this one, right? The idea of how professional astronomers are involved in the actual writing of the code, because that's probably, if you know astronomers, that's the non-trivial part, because of basically this fact, right? So again, in the same survey, we asked a question that probably doesn't surprise anyone too terribly much, but it turns out, despite the fact that astronomers in many ways are software developers, right? 50% of our time is spent writing software, more or less. Most of them don't have, slightly less than half have no formal training in software, and only 10% actually have what they would call real training in software. Right? So 90% of astronomers don't have training, or don't at least have what they consider sufficient training in writing software. Right? So you might ask yourself, given that, how could something like ASTROPY come to be? That would be a good question to ask, but it's important to understand that it has in fact been made to work. Right? So what I'm showing you here is the number of people who've contributed to ASTROPY over time. And really the key element is that not only is it rising over time, but it's a large number, right? There are over 200 people who have contributed code to ASTROPY, most of whom are in some level professional astronomers, many of whom who have never met each other before, right? So it's an important question. How could this happen, given that most of these people at least profess to not be software development experts? Putting it another way, right, getting anyone to work together in astronomy sort of feels like herding cats. But I think this is actually a really good analogy because it demonstrates exactly why this can be made to work, right? This is how you herd cats, right? Anyone who has cats knows that you just have to make them think it was their idea and give them a structure in which to work with, and they'll organize themselves. I think this picture is even more illuminating because of this cat down here, right? This is exactly what astronomers are like. Even when you give them a structure to work with and give them all the tools they need, there's always still, one cat that astronomer who decides, nah, I'm going to go my own way. That's not a bad thing, but it at least means all of these cats are working together. So what does that look like, right? So how do we provide these shared tools that let a large group of astronomers, a large group of people who have this sort of independent mindset work together? It turns out the magic, in many ways, is provided by this tool, GitHub. So probably many of you are at least familiar with GitHub as a place you go to download software, but it turns out it's a lot more than that. It's also a place to go to develop software. On some level, it's driven by the Git tool, a source code version control system. But it's much more than that. It also provides a framework by which anyone, anywhere can contribute to a project. And that is really the magic, in many ways, that allowed this community development model to exist in the first place, much less flourish. So that's basically the key tool. But what does this look like for day-to-day work by astronomers? Well, it turns out it's pretty straightforward using this specific tool called a pull request. This is what has driven essentially all of the development in ASTROPY. We have a very clear policy that essentially everything has to go through one of these things called a pull request, which basically amounts to some random person on the internet who, to be honest, may or may not be qualified, says, I have a change I want to make to ASTROPY. Here is what that change is, and it's all done sort of via relatively straightforward to use tools with lots of documentation. And they say, this piece of documentation in ASTROPY needs fixing, or this function doesn't seem to work for me. I have a change I want to make. I want to request that you pull in my change. Right? That's where the term pull request comes from. So that's what this top part of the website is saying. This random person says, I have found a problem, or I saw a problem with ASTROPY, and I've figured out how to fix it. Here is the change that needs to be made to the source code to make it work. The reason why this is really powerful is because not only can anyone do this at any time, but anyone at any time can then review this pull request. So for example, the immediate follow-on to that person who said, I have some code I want to contribute, is someone else who had more expertise in the code said, this is great, you've definitely contributed something we want, but there's this little problem with it that you need to fix. You didn't follow this element of the style guide, or you didn't do this one other little thing, or whatever. So that's great. The person says, okay, thanks. That was useful feedback. I'll fix it. Then they go ahead and fix it. And then someone else says, there's also this other little thing, right? And these are two totally different people. One who had core commit rights at the time of this paper, who in fact was a space telescope software developer, and another person who at the time this pull request was being written was just sort of a random contributor who happened to know that code well, was involved in working on that code, and could say, here's a thing you need to fix. Right? So this is a very easy and sort of cheap way with just web browsers. You can bring people together from all sides of the globe who have interest in working on this source code. And in fact, many of them can indeed be astronomers. So once you've done this back and forth a few times and said, here's the change I want to make, maybe make this a little tweak. You might even have a little minor argument. But in the end, in practice, almost always there's an end consensus where somebody says, thanks for addressing this issue. Now that you've addressed my concern, everything is happy. And then someone like me, who has commit rights on the source code repository, can just hit this big green button that says merge, and the code becomes a part of ASTROPY. So that's really the key element that makes this community-driven model possible in the first place, is this concept of pull requests, that you can have anyone, anywhere, ask to change the code, have a good, solid conversation using sort of modern web tools, and in the end, with just a click of a button, make it part of the source code. So without this tool set, AstroPy would not have been possible, and all of the sort of modern community open source frameworks would be much more difficult, if not impossible. So really, I think it is this that is the essence of what makes AstroPy a community project, right? Or sometimes it's called a duocracy, where essentially the priorities are set by the people who do the work, right? So this actually, I think I've learned through AstroPy, works in multiple ways, right? It's both, if you do the work of writing the code, your code is more likely to get in, right? It won't get in at all if you don't write it. But also the people who review it, right? A piece of code has to be reviewed. So if one random person says, I want to make this change, and everybody else says, no, that's a terrible idea, then the code will not go through, right? And that's how you want it to work. You want the people using the code to be able to say, oh, thanks for that, but it turns out that's not a good idea, or thanks for that, that's a great idea, here's a minor adjustment to make it better. So that's really the key element here, is that it gives people the power to control the software that they are going to use without having to do all of the work themselves, right? They can pick and choose their area of expertise, their area of interest, and as a result, the priorities of the project develop sort of on their own. Now, of course, it's not like there's no planning of any sort, right? There is a coordination committee, which I'm a member of. We have face-to-face meetings quite regularly. But everything that comes out of those face-to-face meetings has to go through this community process. So all the development happens, is visible to anyone looking anywhere, seeing anything online, and it's just all apparent, right? So if anyone isn't in that meeting and still says, "Oh, wait, I have an idea," they can do that. There's nothing to stop them from doing that. All right. So that's one of the key elements that makes this philosophy possible, right? That makes it possible to make for code to be written both by and for the community, and have those two things talk back to each other, right? The people who write the code are also the people who use the code, and by using this sort of pull request community-driven model, these two can talk right back and forth to each other. If you use the code, you can say, oh, this other person who's writing the code, let me make a small suggestion that makes it better. So that's great, right? That conceptually provides a great way for people to work together very efficiently. But if you're like me, you probably think to yourself, there's no way you could keep track of all of this work, right? No one person can understand what's going on here and make sure it stays stable, most critically, right? And if you think that, you'd be absolutely right. No one person could possibly do this. In fact, probably no N people could possibly do this. Fortunately, we're making use of the much wider ecosystem of the open source community, and one of the things they're really good at doing is making robots, right? So robots can make this task much easier than individual people can. So for the next few minutes, I'm going to describe some of the key elements that make it possible to maintain a stable code base, right? For this sort of community-driven development model to work in a way that lets everybody that makes the code keep working and be useful to a larger set of people than just those people who wrote it. So the first critical element of that is testing, right? So you have to understand that when you write code in AstroPy and using this community development model, a critical piece is that you write tests at the same time, right? You can't just write the code and say, all right, I wrote the code, somebody else figure out whether it's working or not. You write the code, and then you say, oh, I also have to write a little bit of code that checks that, in fact, that code does what it's supposed to do. Most people can do this pretty straightforwardly because Python makes it very easy to write this sort of test. So there's a specific framework on how you run these tests that you'll see in a moment is very critical. But the tests themselves are very straightforward. For this pull request that I've just been showing you, it's 10 lines of code at most, little bit of code that says, here's one input, here's another input, let's run it on this function that person wrote, and if I get the right result, it's good. If I get the wrong result, it's bad. That makes sense, right? That's basically what this code that I'm showing you here is telling you. And the person who wrote the code wrote this alongside the actual code that implemented this piece of ASTROPY, and they contributed it along with the actual code, right? So that's the key element here, is that if anyone provides code, they also have to provide some tests that test that code. The reason why this is critical is because it actually gives you a way to check whether anything that anybody wrote is running correctly, and it's up to them to understand what running correctly means, which is exactly what you want, right? You want other eyes to look at it later on, but you want the person writing the code to be the person who knows it best, to be the one who checks whether or not it's actually working. And then once they've done that, they can just walk away, because we also use something called continuous integration. So the idea behind continuous integration is that all of these tests get run every time anyone makes any sort of change in ASTROPY. So if you were sharp-eyed, you might have noticed this little thing that I have in the red circle here on the pull request that says all is well. That was exactly this continuous integration test running. So every time someone issues a pull request to ASTROPY or anything developed in this mode, a ping goes out to a set of servers run by any of a variety of different services, although most of the ones for ASTROPY are this one called Travis. And it says, run the test for me. And Travis goes and runs the test for you. Of course, it's not a guy, it's a bunch of computers. But the key idea is that this ping goes out to their servers, and their servers run all the tests. You wait 5 minutes, 10 minutes, however long it takes to run all the tests on all of the different, on Windows and Mac and Linux and all this stuff. And then it comes back with a response saying, the test passed, all is well. Or if something was wrong, if that little change you made, it turns out, changed some other piece of code somewhere far away in a different part of ASTROPY, this will come up instead with a red check mark that says, oh, one of the tests failed, and then you have to go back and fix it, right? Now, that's great, because that means you know whether or not you're going to break something, right? Because almost nobody who's contributing to this has any intention of breaking things. We all know we break things all the time when you make just about any sort of change in code. So it's great to get this feedback that says, is it working or is it not working? And this, it turns out, both makes the code more stable and encourages contribution, because once you've got a big code base like this, a lot of people who would otherwise contribute are afraid they're going to break something. But if they have this nice green check mark that tells them, no, you didn't break anything, it's okay, that's one of the very important elements to getting in random contributors who otherwise might be less inclined to be involved in the project at all. So that's one of the two key tools I want to talk about. But the second one is the other, in many ways, key element that makes it possible to have any sort of community-driven code, which is documentation. You need to have some sort of mechanism to make sure the code is documented well enough that someone other than the person that wrote it can understand it. So in ASTROPY, just like most of the Python ecosystem, to do this we depend very heavily on doc strings. So doc strings are just little strings that you write, again, as a part of the code. You write a function, and at the top of that function you put a little piece of documentation, and that piece of documentation, if formatted in the right way, can be run through a particular tool that, again, is very standard in the Python software community, and generates a nice little website that shows you documentation that you can actually read, right? You don't generally find yourself looking at this and saying immediately, I understand what's going on here. But when you look at this documentation, if you look at docs.astropy.org, for example, you'll see a website of documentation that shows you what every function does in a sort of nicely formatted way. So this is, again, the magic is deciding that this is an intrinsic part of the code. That before you contribute a piece of actual new code, not only do you have to write tests, you also have to just make sure you have a standard level of documentation. And once you've done that, it counts, right? But as long as you keep that discipline and make sure some level of documentation, whatever your standards are, some level of documentation is written, then the documentation essentially writes itself, right? It's built into the development process, and you don't get code without documentation. The other key element to make this documentation magic work is simply tools that do the same thing as the continuous integration tools, but for documentation, right? So we have a nice website, but that website doesn't really tell you too much in detail about the code. Instead, you have to go to the documentation itself, either through fancy searches or just by clicking the documentation button. And that takes you to this pretty formatted website that it turns out is always up to date. It's always up to date because of this tool called Read the Docs, which works just like the Travis that I was talking about before. Every time someone makes a change to AstroPy, it pings a server, and that server called on the Read the Docs infrastructure rebuilds the documentation, sends it up to their website, and this all happens without anybody having to do anything manually, right? It's all being done by robots, and those robots are in fact making our lives easier, because that way, every time there's a change, the documentation is immediately up to date. Not only that, but it even stores older versions of the documentation. So if you've installed an older version of AstroPy or something like that, you can just go to Read the Docs and say, oh, well, I can go back to the older docs and see what's going on with my code. So that's the second key element I wanted to talk about, documentation. So to recap, what I see as being sort of the critical elements of making this community-developed software model work are something like GitHub for actually sharing the code, right? GitHub is not actually the only way to do this. I would argue GitHub pioneered this approach, but there are other options. But the key idea is you need some website, some service that makes it easy for random people on the internet who have expertise to contribute code to your code to your code base, and then make it easy for you to take that up and integrate it into your code. Right? GitHub is probably the easiest way to do that in the modern tool ecosystem, but there are plenty of other ways to do that. Any way you can see to do that will work to make this community-driven model operate. The other key element is that you have to be able to test all of the code that someone contributes in some manner automatically. Right? If you don't do that, let's be honest, you're not gonna keep the code up to date. Bugs will start creeping in, and eventually the whole thing is just going to be one hot mess. So you need to keep those tests as part of the development process, and you need to have them run every time someone contributes something. That's the only way to keep a large community cohesive and working in the same direction. And finally, you have to sort of use the same tools, but for documentation. It has to be very straightforward to document the code. It has to be considered at the same level as the code itself, and that will make the code thorough. So these are what I see as sort of the key elements of a community-driven software development model. So you might wonder, how does this work? Well, let's not worry about how it works, because I just told you, instead focus on the fact that it does work, right? Science is enabled by software developed using this process, right? There are many citations to the AstroPy paper, and although software citation is sort of a serious problem because people tend to undercite the concept of software, a better metric is this one: how often people look at the documentation, and that continues to rise at sort of something approximating an exponential rate, depending on the way you look at this. So the key idea is that it does work, right? This community-developed grassroots process that had no monolithic planning board or individual driving the whole thing can still produce code that large numbers of people work on. Not only that, but large projects have now started taking up this sort of community-driven set of software. Right, so this list I'm showing you here is a long list of large projects that use AstroPy on some level or another. And the point is not so much any individual case here, except of course JWST, which I'll be coming to in a minute, but rather to make the point that this code, this community-developed code that sort of has no master on some level, is in fact trusted enough to be used by a whole bunch of large projects throughout the community. Because the community has a sense of buy-in, that it's their software, that if something goes wrong, they can help fix it, right? I think on some level at least, that's the psychology behind this. All right, so before I dive into exactly what that looks like with respect to JWST, I want to say just a little bit more about how it is for the community, in the sense of how AstroPy becomes useful for your day-to-day work. That is to say, what is in AstroPy, right? The key elements are always easy to find on the documentation page, right? So you can always just go to the documentation and look at the long list of functionality. But the key idea I want to get across here right now is just that it covers a lot of different things that are standard tools, right? Standard sort of astronomy things you need to do. It lets you write down things like physical units integrated with astrophysical constants that are important for doing any sort of astrophysics work we all do. It has representations of times and dates that ends up being essentially good to a precision of roughly nanoseconds over Hubble time, right? Which is one of the unique things that astronomy needs, but it turns out can be done if you focus specifically on the interests of the astronomy community. As of course celestial coordinates, so that you can ask this question that I asked at the beginning that sort of motivated the whole thing of how you transition, or how you switch between various coordinate systems that everybody in astronomy recognizes but couldn't agree on a shared set of tools until ASTROPY. It provides some important tools for manipulating tables, most critically, I think, all of the many weird, arcane ASCII table formats that astronomers love to spread around. It provides tools for understanding, for representing and working between different Python software packages with two-dimensional data, right, images, representing that in a way that different tools can use the same data set while not having to all be the same software package is the key idea. It provides WCS, right, a way to map from your pixel coordinates to your sky coordinates, and a whole bunch of other things that I won't dwell on so much other than to point out that they are the day-to-day tools people need to use to do astronomy, right? And all developed in this community model where somebody said, oh, I actually need to figure out, you know, how to convert from redshift to luminosity distance. I know how to do that. I will write a little calculator to do that, contributed in this community developed model, and that is how I will give back to the community. Right? And that's how essentially all of these tools came to be, is that somebody said, I need this, that somebody, in some cases, is just an individual astronomer, in other cases, is sort of a larger group, possibly Space Telescope. But in the end, they were all just being a part of the community and saying, I want to give this code back and work together on making this code better. Right? So those are the key pieces that are in ASTROPY right now. I should also say, right now, bringing it back to JWST, that these key pieces are in many ways part of what makes JWST work. Right? So the framework on which most of JWST's pipelines and all the data analysis tools are built on is, in fact, ASTROPY. Right? So the FITS architecture, or the FITS sub-package is used to load FITS files. Units represent various parts of JWST pipelines and data analysis tools, and so on, right? All of these things that are useful for the community are also useful for JWST, which is exactly what justifies the connection between a large mission like JWST and a community effort like ASTROPY. They have shared interests, right? And because, as I mentioned at the beginning, this whole process is sort of a duocracy. If JWST says they really need to improve the FITS readers, then the FITS readers can be improved because they can put the effort into it. And everybody can do that, right? JWST is just a part of this process. It's not sort of a first-class member of this process, but it can be and has been historically one of the major elements in this process simply because it was needed. So that's sort of how these things connect back, right? JWST has driven a lot of this development, but not as a special monolithic top-down approach, but rather understanding that they are part of the community and a lot of these tools needed go both ways. Now you can learn more if you want and how to use ASTROPY if you haven't used it yourself by following any of these resources I'm showing you here. The easiest point to start from is the tutorials, tutorials.astropy.org, but there's a variety of other mechanisms by which you can learn more. You can also, of course, give feedback on what should be there, either by going to this website, astropy.userecho.com, or by contributing to the code, right? That's sort of the point of this community process, is that you can give feedback, or more effectively, you can turn that interest and that effort into actually helping develop the project. All right, so that's ASTROPY, the core itself. Now I want to turn to talking a little bit about the broader sense of community software that ASTROPY connects back to, but as you'll see in a little while, is even more closely coupled with a lot of the effort going on for JWST. But before I can do that, I have to sort of define a term, right? The term is ASTROPY. Right? I've been talking about this community development model and the ASTROPY package, but now it's important to make a distinction between the ASTROPY package and the ASTROPY project. The reason why is that if you go back to that original vision that I was talking about at the very beginning of this talk, you'll see these were initially laid out as separate things. So the ASTROPY, the core package, is the thing you get in code. When you do pip install ASTROPY or const install ASTROPY, you get a bunch of code that in Python you type import ASTROPY or from ASTROPY import something. That's what the ASTROPY core package is. But it turns out there's now a much larger ecosystem that's enveloped in this ASTROPY project concept that really amounts to the community that surrounds the ASTROPY project, right? The many more domain-specific tools and pieces of code that people need to do the sort of full astronomy workload. And most of it is developed, again, in the same community-developed model. So it falls under the ASTROPY project in part simply because it follows many of the sort of social norms that the ASTROPY core package follows. And these packages are generally known as affiliated packages. So this is basically an astronomy-related package that agrees to be a part of this sort of ecosystem, but is not a part of the ASTROPY core package. Right? For whatever reason, they might not want to be developed on the same time scale, the sort of 6-month clock that ASTROPY development happens, or they want to have their own control over the package, or whatever reason. There are many reasons for wanting to be an affiliated package, but the key point is they sort of agree to follow these standard social norms, or have a common sort of goal and vision of making codes work together better and embrace the sort of coding practices I was describing before that allow community development to happen. There's a full list of them on this website I'm showing you here, affiliated.astropy.org. And this is essentially the only thing that makes it an affiliate package, is that if it's listed there, it's been looked at by the ASTROPY Coordination Committee, which then sometimes asks questions like, are you working together with someone else? But in general, just means they're agreeing and have shown an interest in following these sort of standards and community standards and practices of community development that ASTROPY has. The other thing that turns out to unite them, although it doesn't have to, is this thing called the ASTROPY Affiliated Package Template. So it turns out this is primarily a tool meant to make all of your lives easier. Right? So it's basically a copy of all of the stuff in ASTROPY that makes that community development model work. Right? It's built on sort of the same machinery that underlies ASTROPY, but the key point is that anybody can use it without getting the whole code base of ASTROPY. So it provides this documentation, these documentation tools I was talking about. The same testing framework is set up to operate just sort of out of the box, the same way ASTROPY does. And most importantly, documentation that's very detailed and step-by-step on how you take it from this point to actually all of that stuff I was talking about working. Right? So the key point here is that you don't even have to be an affiliate package to use all these tools, but since we have figured out how it all works, we're giving back to the wider community a sort of pre-packaged set of tools and instructions that let you follow this community development model if you want to. Right, so that's the key point of the package template, is that you don't have to really understand anything about how to do packaging in Python or write documentation tools or testing frameworks. You just have to know that you can follow a set of step-by-step directions, and you can get most of this for free by just dropping your specific science code into one specific place and just turning on all the things. So it turns out this framework seems to have been popular because it's used by a wide range of tool sets now. These range from sort of very specific, domain-specific astronomy packages, like focused on gamma ray astronomy or supernova light curve fitting, to more general tools that are understood to be useful to a wide range of astronomers, but aren't sort of as either stable or standard as the pieces that go into the ASTROPY core package, like say the PHOTUTILS package, which focuses on doing photometry. CCD-proc, which is a tool for doing sort of the same things you do in the IRAF task, CCD-proc, getting from images off the telescope down to sort of science-ready data, interactive visualization tools, and so on. Right? So it spans a wide range of all of the pieces you need to do astronomy with Python, while at the same time while at the same time fitting in this wider ecosystem. All right. And this is what brings us really back to where all the development for data analysis tools, at least, is happening with JWST. Many of them are now being developed as in this framework, this affiliated package template. A lot of these data analysis tools are built that way explicitly to be community-developed projects, to make it easier for the wider community to use JWST by having their own say in the development process of the software, the data analysis tools that go into JWST. So I'm just listing a few of them here, but I'll jump in a little bit more detail into a couple of these. The key idea is that all of these are written using this Astropy affiliated package template and follow, at least at some level, the community software development model. So this leads to the idea of a wider ecosystem that is being developed to make JWST analysis possible. Right, so the whole thing I was talking about before sort of falls under this realm of more external efforts, right? So some of the development work is happening at Space Telescope as part of this community software initiative that powers work on these more broad tool sets that are not necessarily specific to the needs of JWST, but are needed to make all of the other things possible. I've got a whole list of some of the efforts going on here, but more relevant for the remainder of this talk is these data analysis tools, these pieces of code that are going to be important to making JWST science possible, that are primarily developed, or at least many of which now are being developed in this community developed mode. Right, I've got a whole list of those individual packages and efforts going on here. But the key idea is the goal is to make as much as possible of these data analysis tools look something like that. So let me just drill down just a little bit on a couple of these tools and see how the work being done for JWST is being contributed back to the wider community. So one of the specific elements that is most relevant and most complete is the PHOTUTILS affiliated package. So PHOTUTILS was actually imagined at the same time as Astropy as one of the sort of almost core affiliated packages, but it was kept separate because it allows more independent development and a sort of faster pace of progress than what would happen in the core package. And it was also, and has also been embraced by JWST as being the place to put a lot of the data analysis tools, the sort of data reduction efforts beyond the sort of pipeline layer for analyzing imaging data that's going to come out of JWST. So this is sort of what the front website looks like. The key idea is that it looks a lot like the Astropy documentation that I was showing you in the earlier part of this talk. And that's no coincidence. It's been developed using the exact same framework so that the knowledge base that people have developed to make all of this stuff work can be shared, right? You don't have to have a dozen people figuring out how to make the documentation work, just a couple people, because it's all sort of running with the same underlying plumbing. PHOTUTILS is then got a variety of pieces built into it that are developed more or less with JWST analysis in mind, but it turns out that often means it's of general use to the community, right? You might develop a very standard star finder that's used in a wide range of the community, that was even provided as a part of IRAF, and even though this is of course directly relevant for finding stars that JWST instruments will be looking at, it is also really useful to the wider community, right? Even if you don't have JWST imaging, if you have some other kind of imaging and you need to find stars or galaxies in it, the same tool set applies. So by building it in this community developed model, the effort that goes into developing data analysis tools for JWST gets sent much more widely. On top of that, adding additional more developed algorithms that might seem to be specific to JWST can be spread more broadly, right? So this is a more complex version of object finding that does segmentation and all the extra bits you might want to do when you want to go beyond just star finding. That has been developed with applications in mind that might apply to JWST, but are also, again, relevant to the wider community. So even when you go one step further and move beyond what's sort of standard, if you build in this community developed model, these tools can apply to a variety of different contexts. The same holds for the actual measurement, not just object finding, right? PHOTUTILS does more than just finds things. It can also do aperture photometry on them, and can focus, for example, on going beyond, using modern computational techniques that go beyond sort of what some of the standard tools that IRAF provided, moving beyond the limitations of what some of the standard tools that IRAF provided give you, right? So you can decide we're going to go one step further, and with this community developed model, you can then say, all right, let's just put that out there for everyone to use, right? You don't have to spend a ton of time deciding which is the right one. You just say, we're going to provide a variety of different methods, and you can decide for your particular use case what works best. And then JWST can just focus on providing sort of the right set of defaults to make it work for the JWST instruments. Right. Running a little low on time, so I'll skip past that. And then focus on one final tool that's being developed as part of the data analysis tools effort as a similar example of how work that is nominally for JWST is useful for the wider community. So this is the SPECVIZ tool, which is exactly what it sounds like, right? It's a spectrum visualization tool. It's been designed with the needs of the various spectroscopic capabilities of JWST in mind, but most of those same needs apply to any other effort to analyze a spectrum, right? You look for some absorption line, you fit that absorption line, and you learn something that way, right? You look at your data very quickly. You want to be like, is this what I think it is? I'll fit a few lines, sort of a quick look mode. And that is certainly what you want to do the day you get your first JWST spectroscopic data set, but it's also exactly the first thing you want to do when you're sitting at the telescope at a ground-based instrument and asking, do I have good enough signal noise to move on, right? Those tasks, it turns out, are in many ways the same task, and if you make this software community visible, community developed, it can be made to work just as well for either of those use cases. So the key idea then is that all of these tools that are being developed as part of the data analysis tools effort at JWST are meant to be community software, right? They don't necessarily have the same number of contributors as a large package like ASTROPY, but they to a variety of different extents are community packages, right? Some of them are developed, have enough contributors that are totally unassociated with JWST that they really are actively developed by multiple people at the same time and represent the broader interests of the community. So that's the sort of direction things are going. If you think, any of you out there, more so on the internet than the people in the room, I guess, but want to get involved in these efforts, bear in mind that the first way you should do this is to just start trying out some of these tools on your own data, right? To get in the spirit of community developed software, the first thing you have to do is just start playing around with it. If you have issues, you might report them on GitHub. And if you really want to, you can then contribute code back using this same community developed model. If you find problems and you know how to fix them, you can just do it, right? You don't actually have to follow some long and complicated process of waiting for someone to fix it, and then it turns out they didn't really understand what you meant. Instead, you can just go in and fix it. And that is perfectly fine, in fact, encouraged in this community developed model. And that works the same for these data analysis tools that JWST is developing as it does for the wider ASTROPY ecosystem. If you're also interested in more active development, you might consider signing up for the Data Analysis Development Forum, which is a way to solicit sort of community feedback and discussions and do more focused coding sprints on some of these tools. The link is shown right here. But the key idea is, even if you don't do that, you can take part in this community developed model. So then the final thought I want to leave you with is the basic idea that this model applies well beyond JWST, but it is also it can be a critical element to making JWST science happen. Right? The key idea here is that if you want to follow this community development model, you can use it to develop specific science domains, right? If there's a particular area of JWST you're interested in, near field cosmology, you can start following this community development model, community developed model, and build Python packages that work extremely well within this whole framework, and maybe even make it a part of your ERS program. That would be a great way to contribute back to the community in terms of software, make science more possible with JWST, and in the end, help us all as a community move forward together. Thanks for your attention.
Does anyone have any questions for Erik?
If not, you can be distracted by this fun movie of the development process.
Nice movie, I like that. So can you say a little bit more about documentation, and specifically, often when I encounter documentation about code, it's at a very atomic level, like what are the arguments, what do they mean, it returns this, and nothing about the higher level thing of what's the context, why would you use this software, what are its limitations, and so on. And is there any, first, is there any requirement for that, and secondly, is it reviewed in some way?
Yes, so the question is sort of, is there narrative documentation as opposed to specific function level documentation? Yes, absolutely. And at least in ASTROPY and in many of the affiliated packages that are sort of built on this model, the expectation is not just that every function be documented, right? That I emphasize that as being a key piece because that's a piece that's often missed in other languages where this isn't sort of baked in. But it's absolutely critical that there be some form of narrative documentation that says, here's the story, here's why you would use this. So ASTROPY has this, and it's one of the beautiful things about that Sphinx tool I was telling you about is that it lets you interleave these two things. It lets you have sort of the code level documentation mixed in with a story that says, here is why this particular submodule, this particular affiliated package is useful, here are the areas where it works, and here are the areas where it doesn't. And the expectation is, for example, when an affiliated package comes up for review, we actually look at that and ask, could some random person go to this website and understand what this code is doing? If the answer is no, then it has to improve before we would accept it as an affiliated package. So it's absolutely a part of the critical element of deciding, is this in the community developed model?
Any other questions for Erik? If not, I think there are a few online participants. I think they're all on mute, so if you have any questions online, please feel free to unmute yourself and ask your question. Okay, I guess if there's no other questions, let's just thank Erik once again.